All right, let's jump right in. Today, we're going to tackle one of the biggest, most fundamental questions in all of robotics. It's a problem that every single moving machine has to solve to be useful. It sounds so simple, right? Where am I? But as you'll see, the answer is anything but.
So, take a look at our little robot friend here. Just like you or me, it's got to know where it is to get around. It's holding a map, it's looking around, spotting landmarks. See that clock tower? It uses all that info to figure out its exact spot. And that whole process, from sensing the world to finding its position, that's what we call localization.
You know, to really get what the robot is going through, just imagine this. You wake up in a room you've never been in before, and it is pitch black. What do? You probably stick your hands out, right? Feel for a wall, listen for any sounds. You're trying to build a mental map. Well, that is almost exactly what a robot is doing, just with its own set of high-tech sensors and a whole lot of math.
Okay, so let's get a nice, clean definition on the table. Robot localization is simply the process a robot uses to determine its position and its orientation, which way it's facing, inside an environment it already has a map for. And this is absolutely crucial. Without it, a robot can't follow a path, it can't dodge things, it can't do its job. It's really the starting block for everything.
So, to really understand localization, it actually helps to see what it isn't. There are a couple of other big challenges in robot navigation that are closely related. So the question becomes, are we just trying to find where we are? Are we trying to draw the map? Or, and this is the tricky one, are we trying to do both at the same time? And this table here lays it all out perfectly. Let's break it down. For localization, the robot already has a map of the world. The only thing it doesn't know is its own position on that map. Simple enough. For mapping, it's the total opposite. The robot knows where it is, but the map of the world is the big unknown it needs to figure out. And then you have the beast, SLAM. This is where the robot starts with literally nothing. It has to build the map from scratch while figuring out its own position on that very map it's building. It's a huge challenge. And this image really drives the point home. Look, on the left, you've got localization, which is just asking, where am I? In the middle, mapping is asking, what does this place look like? And then all the way on the right, you see SLAM, which is that ultimate chicken and egg problem, right? You need a map to know where you are, but you need to know where you are to build a good map. How do you even start to solve that?
Okay, so how on earth do robots actually pull this off? Well, here's the secret. They never know their position with 100% certainty. It's just not possible. Instead, they work with something called a belief. And a belief is basically just a really educated guess, a probability of where they think they are.
And there are two main kinds of uncertainty a robot is always dealing with. If you look at the image on the left, that curve represents the robot's belief about where it is right now. If that curve is really tall and skinny, the robot is pretty darn sure. If it's wide and flat, well, it's not so sure. Now, check out the image on the right. This is what happens when the robot just moves. Even a simple turn isn't perfect, and those little errors cause its uncertainty to grow and stretch out into this kind of funny banana shape. So robots have a couple of main ways to keep track of this belief. The first is what we call a continuous belief. Think of this as putting all your eggs in one basket. The robot makes one single best guess. It's super efficient, but hey, if that one guess is wrong, the robot can get hopelessly lost. The other approach is a discrete belief. This is more like hedging your bets. The robot tracks a whole bunch of possible locations at the same time. It's way more reliable, but you can probably guess the downside. It takes a ton more brain power, a lot more memory and processing.
Okay, so if the robot is always a little bit uncertain, how does it ever actually figure out where it is with any confidence? How does it lock in its position? Well, this is where we get to the secret sauce. There's this really powerful mathematical loop that lets a robot take all that messy, uncertain information and distill it down into a single, precise location.
And it really all boils down to a super simple two-step cycle that just repeats over and over again. Step 1 is predict. The robot moves, and just like we saw with that banana shape, its uncertainty gets bigger. Then comes step 2, correct. The robot sees something it recognizes, a landmark, and that new piece of info lets it shrink its uncertainty back down. So it's just this constant dance. Predict, grow uncertainty. Correct, shrink uncertainty. Over and over and over.
And this diagram shows that cycle in action. This whole process is called a Bayes filter. So look at the top part. The robot moves forward, and you can see its belief, that orange blob, gets wider, more spread out. It's less certain. That's the prediction step. But then, in the bottom part, its sensor spots a landmark.
That observation is a new piece of the puzzle. It combines what it thought with what it now sees, and bam, you get that much tighter, more confident blue curve. That's the correction. It's pretty cool, right?
Okay, so this predict-correct cycle sounds almost foolproof, doesn't it? But, the real world is messy. It's not a clean laboratory. And there are some really tough challenges out there that can throw a huge wrench in the works and get a robot completely confused.
Think about it. This whole system hinges on one critical assumption, that the robot's sensors are telling the truth. But what happens when they lie? What happens when a robot's sensors get tricked and two totally different places look exactly the same?
Well, that's a classic, tricky problem in robotics, and it has a name: sensor aliasing. Just look at this situation. Our robot is at a fork in the road, but both hallways look identical. Its camera sees the same thing. Its laser scanner, the LiDAR, gets the same distance readings. As far as the robot is concerned, these two spots are completely indistinguishable. It has absolutely no way to know if it should go left or right. And in that moment, its whole localization system can just break down.
So, let's bring this all home. The next time you see one of those robot vacuums just cruising around a living room, making it look easy, I want you to remember everything that's going on under the hood. It's not just randomly bumping into things. No way. It is constantly running this incredible, complex dance of predicting, correcting, and battling with uncertainty, all to solve that one seemingly simple question: where am I?